After studying this model, you will be able to know more about irreducible representations, learn about Great Orthogonality Theorem, rules derived from Great Orthogonality Theorems, and rules about irreducible representation of the point groups. Examine now the correctness of these rules by taking suitable examples. Learn how to check the irreducibility of a representations and examine the correctness for the equation for irreducible representations. That is, you will be now looking for how to find irreducible representations and what is the relation between irreducible and reducible representations, and here the Great Orthogonality Theorem will help us in this direction. Earlier we have seen the importance of reducible representation and relation between reducible and irreducible representation, various methods of getting or generating reducible representation. There are several special basis sets for representation, and for reference these can be unit vectors along Cartesian coordinates, that is Tx, Ty, Tz, rotational vectors Rx, Ry, Rz, binary Cartesian functions xz, xy, yz, and so many vectors directing along the various bonds, wave function of the molecule. So, there can be infinite ways in which we can represent or we can generate the representations. How are the irreducible representation important? The vibronic and electronic wave functions can be used to generate the irreducible representations. These irreducible representations are very important in dealing with vibrational spectra, chemical bonding problems of transition metal complexes. Earlier it is seen that how large reducible representation can be obtained using infinite number of basis function. In this module, we will examine the relation between reducible and irreducible representation. How to get irreducible representation without following a lengthy procedure. Identification of whether the representation is reducible or not is time consuming. In this module, systematic approach will be followed. All the properties of a group irreducible representation and their characters, which are very important in solving problems concerned with chemical bonding and molecular dynamics, can be derived from one basic theorem which takes into account the relation between matrices elements of the irreducible representation in the reducible representation. Great Orthogonality Theorem. The central role of the theorem is that it provides the criteria for determination of irreducibility of a reducible representation and also gives the number of non-equivalent irreducible representation into reducible representation. Great Orthogonality Theorem. In this module, I will give only the statement about the theorem and important rules that can be derived from the theorem. No proof for these statements will be attempted in this model. Now, the theorem mathematically can be stated as given in equation 1, and this equation 1 Great Orthogonality theory can be decomposed into three different equations, equation 2 and equation 3 and equation 4. Now, these four equations, equation 2, 3 and 4 can be used to derive certain simple rules which can be used to find correct relation between reducible and irreducible representation. Now, without going into the detail of all the theorem or equations which are mentioned above, I will just state the rules and let us try to explain these rules. Now, rule number 1, the dimensionality theorem. The sum of the squares of the dimensions of the irreducible representation of a group is equal to the order of the group. If the dimension, that is, if the summation Li square is equal to L1 square plus L2 square plus L3 square like this is equal to H, where Li represents the positive integer and represents the dimension of the irreducible representation. Let us examine this rule. Take the C3V point group which has 6 symmetry operation in it. So the order of the group H is equal to 6. Character of E gives the dimensions of the representation. That is, the dimension is 1, 1 and 2. For A1 it is 1, for A2 it is 1 and for A is equal to 2. And the last column gives Li square. That is, dimension 1, 1 square is equal to 1. A2 dimension is 1, square is 1. Dimension of A is 2 and its square is 4. So 1 plus 1 plus 4, that is equal to 6. That is, it is the order of the group. Since character of E represents dimension of the irreducible representation, the equation 5 can be rewritten as summation I chi I E square is equal to H. That is, we can directly make use of this equation to find this. Second rule is the sum of the squares of the characters of the matrices corresponding to operation R in ith irreducible representation equals to the order of the group. That is, summation R chi R square is equal to H. That is equation 7. Let us take C3V character table and take any of the reducible representation. We take A1 representation and apply this equation. What you get after applying this equation? 1 square plus 2 into 1 square plus 3 into 1 square is equal to 6. Here we have to multiply the total number of operation in a class. That is, here H is the order. Then rule number 3. The vectors whose components are the characters of the two different irreducible representation are orthogonal to each other. That is, summation R chi I R and chi j R is equal to 0. That is, I not equal to 0, equation 8. And again, let us take A1, A2 irreducible representation in C3V table and apply the equation number 8 over here. On applying equation number 8, we get 1 into 1 plus 2 into 1 into 1 plus 3 within bracket 1 into minus 1 is 0. Rule number 4. In a given reducible or irreducible representation, the character of matrices corresponding to operation belonging to the same class are identical. That is, in a class, all matrices have same chi value. Rule number 5. The number of irreducible representation in a group equals to the number of classes in that group. For example, in C3V group, the number of classes are 3. So, it has 3 irreducible representation. Rule number 6. One-dimensional representation in which all the characters are as one is called totally symmetrical representation, and this irreducible representation will always be present into the irreducible representation of the point group. Rule number 7. Characters of an irreducible representation of a point group are independent of the choice of basis taken for the irreducible representation. The rule number 8, the number of irreducible representation, that is AI, is given by the equation number 9, that is AI is equal to 1 upon H summation over all classes NR chi R into chi JR. So, by making use of this equation, you can find out how many irreducible representations are present into a particular representation. And in order to explain, you can take the example of D3 point group. It has E, 2C3 and C3 symmetry operation in it. So, in total there are 6 operations. Thus, the order of the group H is equal to 6. There are 3 classes in it, E, 2C3 and 3C2. So, there will be 3 irreducible representation in this group. And let this be T1, Ta1, Ta2, Ta3. And let the dimension of this irreducible representation is L1, L2, L3. And according to the rule 1, L1 square plus L2 square plus L3 square is H is equal to H, and here it is equal to 6. Only one possible value of these dimensions are L1 is equal to 1, L2 is equal to 1 and L3 is equal to 2. In general, there is one totally symmetrical irreducible representation in which chi value for all symmetry operation in a class are ones. Rule 6, thus we can write down the D3 table as D3 operations are E, 2C3 and 3C2. Ta1 is 1, 1, 1, and these satisfy our equation summation R chi R square is equal to H. And also L1 square plus L2 square plus L3 square is equal to 6 is also satisfied, that is 1 into 1 plus 2 times 1 into 3, 2, 1, 3 into 1 is equal to 6. So, like this we have the Great Orthogonality Theorem which can satisfy the relation between irreducible representation and irreducible representation. Now, look for a vector in 6-dimensional space whose components are equal to plus minus 1 and orthogonal to Ta1. Components of vector must contain 3 plus 1 and 3 minus 1 as the character. Since chi E is always positive integer and also all operation in the same class must have the same character, the only possibility for Ta2 with L2 is equal to 1, which is orthogonal to T1, and our D3 point group now looks as Ta1 is 1, 1, 1 and Ta2 is 1, 1 and minus 1. And we can examine the orthogonality of T1 and 2, that is 1 into 1 plus 2 times 1 into 1 plus 3 times 1 into minus 1, that is 0. That is, third irreducible representation will be of dimension 2, L is equal to 2, and we know the character for chi is equal to 2. Let the character for C3 is chi C3 and character for C2 is chi C2, and by putting this we can complete the table as given over here. That is, Ta3 is 2, then chi C3, then chi C2. The values of chi C3 and chi C2 can be easily obtained by taking the rule of orthogonality. That is, we check the orthogonality of Ta2 and Ta3, then check the orthogonality of Ta1 and Ta3, and thus we will get two equations, and by solving these two equations we can get the values of chi C3 and chi C2, and by getting this equation 10 and equation 11 we get the values of chi C2 and chi C3, and after getting these values chi tau 3 comes out to be 2, minus 1 and 0. So, correctness of this can be easily checked. 2 square plus 2 into minus 1 square plus 3 into 0 square is equal to 6. That is, we can check. Now, another important property, criteria for irreducibility. It can be easily worked out whether a representation is reducible or irreducible without going into the proof. If a representation satisfies the equation 13, that is summation r nr chi r whole square is equal to h, then the representation will be irreducible, where nr represents the number of symmetry operations in a class. And now all these rules which I have been stated and explained in terms of D3 point group can be easily verified. If I take a D3 point group and take tau 5 as shown into the table, tau 5 is 5, 2, minus 1, and we can verify, that is, whether this is reducible or not reducible by making use of equation 13. You will find it is a reducible representation. If I take tau 1 D3 point group and go for the equation 13, you will find it is irreducible representation.
After reaching to this point, now, for us there is a great need to study Great Orthogonality Theorem. All the properties of a group, irreducible representation, and their characters, which are very important in solving problems connected with chemical bonding and molecular dynamics, can be derived from one basic theorem, which takes into account the relation between matrices, elements of the irreducible representations in the representation, Great Orthogonality Theorem. The central role of the theorem is that it provides the criteria for determination of irreducibility of a reducible representation, and also gives the number of non-equivalent irreducible representations in a reducible representation.
Wherever complex or imaginary numbers are involved, it is necessary to take the complex conjugate of one factor on left-hand side of the mathematical statement of the theorem. This is the left-hand side of the mathematical representation of the Great Orthogonality Theorem. Right-hand side of GOT is. This equation is denoted as equation 1. In the set of matrices which constitutes any of the irreducible representation, this set.
Making use of 2, 3, 4 equations as depicted in the video of mathematical representation of Great Orthogonality Theorem, some simple rules regarding irreducible representations and their characters have been derived from Great Orthogonality Theorem. These rules are quite simple and can be easily used for correlating irreducible and reducible representations. The first rule is the dimensionality theorem, which says that the sum of the squares of the dimensions of the irreducible representations of a group is equal to the order of the group. The equation is denoted as equation number 5. Let us now examine this rule. Take a C3V point group which has 6 symmetry operations in it. So the order of the group H is equal to 6. Character of E gives the dimension of the representation. The dimension is the character for E in an irreducible representation. Here these are A1 equal to 1, A2 equal to 1, E equal to 2. Therefore, 1 square plus 1 square plus 2 square equal to 6. Since character of E represents dimension of the irreducible representation, the equation 5 can be rewritten as equation 6. The second rule says that the sum of the squares of the characters of matrices corresponding to operation R in the ith irreducible representation equals to the order of the group. The equation is denoted as equation 7. Let us now take C3V character table and take any of the reducible representation. We take A1 representation. One key point to be kept in mind is that total number of operations in a class must be taken into account. The third rule depicts that the vectors, whose components are the characters of two different irreducible representations, are orthogonal to each other, and the equation is denoted as equation 8. Let us examine A1 and A2 irreducible representations from C3V character table. Here, it's clearly seen that 1 into 1 plus 2 times 1 into 1 plus 3 times 1 into minus 1 equal to 0. The fourth rule says that in a given reducible or irreducible representation, the characters of matrices corresponding to operations belonging to same class are identical. That is, in a class, all matrices have same chi value. The fifth rule denotes that the number of irreducible representations in a group equals to number of classes in that group. The sixth rule says that one-dimensional representation in which all the characters are as ones is called totally symmetrical representation and will always be there in a group. The seventh rule is that characters of an irreducible representation of a point group are independent of the choice of basis taken for this irreducible representation. The eighth rule says that the number of irreducible representations AI is given by the equation 9. You are already aware of the symmetry operations present in D3 point group, that are E, 2C3 and 3C2. In total, there are 6 operations. Thus the order of the group H equal to 6. There are 3 classes in it, E, 2C3 and 3C2. So, there will be 3 irreducible representations in this group. Rule 5. Let these boxes be tau 1, tau 2, tau 3. Thus we can write D3 table as shown.
Slide 20. D3 point group has E, 2C3 and 3C2 symmetry operations. In total, there are 6 operations. Thus, The order of the group H is equal to 6. There are 3 classes in it. So, there will be 3 irreducible representations in this group. Let these be tau 1, tau 2, tau 3. Let the dimensions of these irreducible representations be L1, L2, and L3. And now,
It can be easily worked out whether a representation is reducible or irreducible. Without going into the proof, if a representation satisfies the equation 13, then the representation will be irreducible, where NR represents number of symmetry operations in a class. Let us take tau 1, tau 2, tau 3 irreducible representations of D3 point group, the characters for which we just worked out and checked the irreducibility, and others are as given in the table. For tau 1, equation 13 can be written as given, which proves that tau 1 is irreducible representation. Similarly, for tau 3, results are as given. It proves that tau 3 is irreducible. Now, let us examine tau x for its reducibility or irreducibility. The result is not equal to h, so it is reducible and can be reduced further. Like this, one can test reducibility or irreducibility of a given representation. At
In this module, what we have learned more about irreducible representation. We have learned about Great Orthogonality Theorem, its statement, and its decomposition into 3 simpler equations, and then we have stated the rules derived from these equations, and these rules have been explained by taking C3V point group and also D3 point group table. Now, criteria for irreducibility of a representation was discussed and explained with the help of D3 point group, and it has been checked that tau 1 is irreducible and tau 5 is reducible, and number of other examples have also been discussed in these modules on the e-text.